All right, let's get right into it. Today, we are diving into a really fascinating scientific paper, one that takes a bold shot at physics that's been established for over a century. Think of it like a scientific title fight, a classic challenger stepping into the ring against a heavyweight champion. Only this time, the ring is the hydrogen atom itself.
So let's just kick things off with a huge question. What if everything we think we know about the atom, the basic building block of you, me, and literally everything, is actually flawed? That is the seriously provocative idea at the very heart of the research we're exploring today.
Okay, so let's really set the stage here. And look, this is not just some minor academic debate. The paper we're looking at throws a direct challenge at the very foundations of modern physics. So in one corner, weighing in with nearly 100 years of victories, you've got the undisputed champion, quantum mechanics. And in the other corner, we have a brand new challenger, something called the deterministic theory of the atom, or DTA for short. It is a true David versus Goliath story, and it all boils down to one single experiment.
And let's be super clear about what's on the line here. This isn't just about some complicated formulas on a whiteboard. The outcome of this could challenge the fundamental rule book that we thought governed our entire universe on the tiniest scales. So you might be wondering, how on earth do you even test a theory of the atom? Well, you kind of have to see it in action. And that brings us to the battleground for this whole debate, an incredible experiment from 2013 that basically managed to take a photograph of an atom's orbit. The fancy name for the technique is photoionization microscopy. But in simple terms, here's the play-by-play. Scientists took a single hydrogen atom, and then, step 1, they zapped it with a laser to get its electron all energized and excited. Step 2, they used an electric field to basically knock that electron loose. And finally, step 3, they projected the electron's path onto a detector. And just like that, you've got a snapshot. And out of all that amazing science, the whole thing boils down to one single number, 1.4. When they measured the size of the electron's orbit before and after the laser zap, the ratio between the new, excited orbit and the original one was 1.4. You have to remember this number. Everything, and I mean everything we're about to talk about, hinges on it. All right, so we've got our piece of evidence, the number 1.4. It's locked and loaded. Now, the paper lines up 3 different atomic models to put them to the test. So let's meet our contenders. First up, we've got the old-timer, the classic, Niels Bohr's model from way back in 1913. Now, this model pictures electrons circling the nucleus in these very specific fixed orbits, kind of like planets around the sun, but on set tracks. It was a hugely important first step, but for the most part, physics has moved on. Next, the heavyweight champion of the world, quantum mechanics. I mean, this theory is an absolute beast. It's the most successful scientific theory in history. It's the reason your phone works, it's how we understand stars, the whole shebang. But here's the weird part about it. It says you can never know exactly where an electron is. It's more of a fuzzy probability cloud where the electron is most likely to be. And finally, here's our challenger, the deterministic theory of the atom, or DTA. What's so wild about this one is that it just throws out all that weird, fuzzy quantum stuff. No probability clouds. Instead, it tries to get back to basics, using the old school physics of people like Newton. It is a completely different way of looking at the problem.
Okay, this is it. The moment of truth. We have the number from the real-world experiment, that magic number, 1.4. And we have our 3 theories. So the paper asks a really simple question. Which theory's prediction actually matches what happened in the lab?
So, who wins? Is it going to be the old classic, Bohr's model? Is the reigning champ, quantum mechanics, going to keep its title? Or does the new kid on the block, DTA, manage to pull off a major upset? Let's check the scoreboard, straight from the paper. Okay, you might want to sit down for this. The experimental number was 1.4. Bohr's model, it predicted 900. Not even in the same ballpark. Quantum mechanics, the champ, it predicted 591. Whoa, again, way, way off. And then you have DTA, its prediction 1.33. I mean, the numbers on the right tell the whole story. The established theories are off by tens of thousands of percent. DTA is off by just 5%. It's stunning.
Let's just pause on that for a second. The numbers in that table are so starkly different, it's almost hard to wrap your head around. According to this paper's analysis, the mismatch between the standard theories and the real-world experiment isn't just big. It is absolutely colossal. And this bar chart just says it all, doesn't it? Look at that tiny little sliver for DTA's 5% error. You can barely even see it. And then, look at the other two. The bars for quantum mechanics in the Bohr model literally shoot off the top of the chart. We're talking about deviations of over 42,000% and 64,000%. This visual really drives home the paper's central claim.
And the paper itself puts it pretty bluntly. The authors say that DTA's prediction just flat out significantly outperforms the established models. And why? Well, they argue it's because DTA sticks to classical, straightforward rules about energy conservation, and it doesn't get tangled up in the probabilistic ideas that, according to them, led the other models so far astray. So, what does all this mean? Where do we go from here? If this one paper, based on this one experiment, shows such a massive discrepancy, what are the implications? Well, according to its authors, they are nothing short of profound.
Yeah, the paper really doesn't pull any punches in its conclusion. It basically says, look, DTA worked better here. It claims this result challenges whether we even need some of those weird quantum assumptions. And it suggests this could be the start of a huge paradigm shift, maybe even a return to more deterministic classical models of the atom. It's a bold, bold call for a total re-evaluation of modern physics.
And that leaves us with this one final, fascinating question. This paper presents a really compelling, data-driven argument that seems to put a crack in a century of physics. But is one experiment, no matter how precise it is, really enough to rewrite the rules of reality? That is the huge question this research leaves for the entire scientific community to think about. Thanks for diving in with me on this one.